Alright, so we're going to jump into Chapter 4 here, dealing with 4.1, 4.2, and 4.3. It's a lot to cover in this first lesson, but it should go by pretty easily. So, 4.1 talks about randomness, probability, and simulation. So for probability, we're looking at proportion of times the outcome occurs in a very long series of trials. Okay? Proportion of times the outcome occurs in a very long series of trials. That's what probability is referring to. Now, the second thing we're going to talk about today as well that comes into play is the law of large numbers, to where in more and more repetitions, the proportion gets closer to its probability. So if you're saying I've got, there's a 50% chance that something's going to occur, the more and more repetitions you do from the samples, right, of actual surveys of population, the closer it will get to that actual probability of 50% of whatever you're trying to achieve, right, if that's what it's supposed to be. But we'll go into that more as well. The third thing in the 4.1 they talk about covering is simulation, which is your state, plan, do, and conclude. Now those are mainly three steps we're going to touch on more in the future, dealing with problems as they get more advanced, and as far as the steps we need to follow to actually come to a conclusion, an actual answer for a specific simulation. Then we're going to jump into 4.2, which is basic probability rules, and we'll talk about a sample space, right? A list of all possible outcomes with a probability. So in other words, we'll do examples of tables or tree diagrams. And the trick to that sample space when we're talking about these tables or tree diagrams is the probabilities will all add up to 1. Or if you want to think about probability in a percentage, in other words, it add up all to 100%. That's the key thing there, and a good fail-safe to check on is if it all adds up to 1 or at least 100%. However you're doing your probabilities, either in percentages or in decimal values. We'll also talk about the complement rule, which is talking about a complement of a setup, so you're taking whatever is going to not exist out of 100%, right? So therefore it's just getting what's left. If you're saying you have a probability of winning the lottery, well, the complement is your probability of not winning the lottery. So as far as you're looking for the complement, it's whatever is not the probability you're looking for. Then we'll talk on something that a lot of people kind of get confused with a little bit. It's called mutually exclusive. Okay, mutually exclusive there is two events with no outcomes in common. So in other words, they cannot occur together. So with that, this equation will make a little more sense as we get to problems. A mutually exclusive equation is using probability of A or B, and that equals just the probability of A plus the probability of B. And we'll talk about that in an example to make a little more sense as far as the probability in general, because if you have probability of A or B and it's not mutually exclusive, the equation, there's one extra thing you got to put into that equation. We'll talk about it. For 4.3, we're going to look at two-way tables and Venn diagrams, and this will make a lot more sense, especially talking about the mutually exclusive when we get to play with this. Dealing with if you have probabilities of A and B and not A, and how that plays out, and therefore how to actually put that into a Venn diagram. Hopefully most of you all have already seen a Venn diagram in other courses, in which case you have your two big circles and where they overlap. Where they overlap is where both occur. So and the number correlation is there as far as the two-way table that's listed on how those numbers would play out. And then as far as your OR statement, as I was mentioning, there's one extra step you got to put in there. So if you just have a regular probability of A or B, then you would simply take the probability of A plus the probability of B and subtract the probability of A and B, so that you're not counting it twice. However, if it's mutually exclusive and two things cannot occur at the same time, therefore that's what it's meaning you don't have to subtract that probability of A and B, because they cannot occur at the same time. They cannot occur together, so there's no reason to subtract a probability of A and B. It may still be a little bit confusing. We'll get into that, and hopefully the example we go over makes a little bit more sense. Alright, so let's jump into this real quick. let's say on randomness, probability, and simulation. So we're going to do 4.1 here and go through some problems here and make sure everybody's got a good understanding of what we're doing. So in New Jersey Transit claims that its 8 a.m. train from Princeton to New York has a probability of 0.9 of arriving on time. So it has a 90% chance of arriving on time. Assume for now that this claim is true. So it's telling us it goes from Princeton to New York. That train has a probability of 90% of the time arriving on time. And we're to assume that this is true. So it wants us to explain the probability of 0.9, what it means in this setting. And I've kind of already answered this with trying just to read the actual problem to you. In which case I'm saying if you take many samples of the 8 a.m. train, so the train leaves at 8 a.m., you do many samples, about 90% of them will arrive on time. So that's why it's meaning 0.9 arriving on time. 90% of them will be on time. So then it goes into the 8 a.m. train has arrived on time 5 days in a row. So it's got 5 days in a row. What is the probability that it will arrive on time tomorrow? Well, if you think about this, it's still 90%, right? It doesn't mean that anything has changed in what is going to happen for the next train. Okay, so the train arrived 5 days in a row. Well, that's great. So what's the probability that it arrives tomorrow? Well, that train still has a 90% chance of arriving on time. It said that initial problem. We assume that's true, that if a train leaves at 8 a.m. from Princeton, New York, the probability of arriving on time is 90%. So it still has that 0.9 or 90% chance. The short run does not change the probability of the next train. So it doesn't change the probability of the next train just because that one train right on time. Or even if it didn't. If, let's say, the 6th train doesn't arrive on time, that doesn't affect the 7th train that takes off and goes there. It still has a 90% chance of arriving on time. So now, on number 3 here, it says a businessman takes the 8 a.m. train to work on 20 days in a month. He is surprised when the train arrives late in New York on 3 of the 20 days. Should he be surprised? Describe how you would carry out a simulation to estimate the probability that the train would arrive late on 3 or more of the 20 days in New Jersey's transit claim is true. Do not perform the simulation. So I don't want to perform the simulation, but just talk about how it should play out. So to carry out a simulation, let's go ahead and just take 10 numbers here. So we'll let 1 through 9 be on time. So we'll label 10 trains, and 1 through 9 we'll say to be on time, and the 10th will be late. Alright, so that's what we're going to set up for before we go into our random number generator, right? So we're going to say we've got the numbers 1 through 10, and if that number lands on 1 through 9, then the train's on time. If it comes up as a 10, then that's going to be the late train, okay? So we're going to use a random number generator to get the numbers between 1 and 10. And we'll do that 20 times to simulate the 20 train rides. And to see if his complaint was worth the effort or not, we'll keep track of the number of trains that were late, the number of times it was late, right? So that's how you would set up a simulation to do this, okay? So again, we're just labeling the numbers 1 through 10. So for that, 1 through 9, the trains will be on time. And if we get the number 10, that means that train was late. We use our number generator again, we do that 20 times, and that's how we keep track of the trains that are on time and that are late. Going into number 4 here, the dot plot shows the number of days on which the train arrived late in 100 repetitions of the simulation. So they did the simulation, okay? So what is the resulting estimate of the probability described in question 3? And should the businessman be surprised? So looking at this, we should already see that possibly not, maybe so. Let's look at it. Alright, so with this, if we were to go in here and count these dots, right? So with this it says, dot plot shows which days the train arrived late in 100 repetitions. So In problem number 3, it said out of 20 days, it arrived, 3 of them were late, right? 3 of the 20 days were late. So let's look number of days, or number of late arrivals. So if we were to count from late arrivals of 3 all the way to 7, we're going to count all those dots up, which I already have counted them up, and they're actually 30 dots, okay? It's 30 dots. So, with this, for the probability of being late 3 or more times, right? Let's write that a little bit better. 3 or more, right? So, probability of being late 3 or more, that's going to equal, as we had, 30 dots. 30 dots out of 100, right? 30 dots out of 100. So that gives us 0.3, right? Or you could simply say 30%. So 30%. So with it being 30%, he shouldn't be that surprised his train was late 3 times, because 30% isn't unlikely, okay? So it could happen. Again, there's just a 90% chance of it arriving on time, but it still can be late, okay? And out of the simulation that we did 100 times, there were 30 of them that were late, 3 or more, okay? So with that, he shouldn't be that surprised his train was late 3 times. 30% isn't unlikely. So now we're going to go into 4.2, talking about basic probability rules. So on our basic probability rules, we're going to look at, okay, let's go back up here real quick to our big ideas. On basic probability rules, we're talking about sample space and our complement equation, and talk about mutually exclusive and how that plays out. Right? So, with basic probability rules, so how prevalent is high cholesterol? We choose an American adult at random and define 2 events. Okay, so A, the person has a cholesterol level of 240 milligrams per deciliter of blood or above. So A is 240, they have that, equals 240 or above. And B is the person has a cholesterol level of 200 to less than 240. Okay, so 200 up to 240, but doesn't actually touch 240. So anywhere from 200 almost up to 240. Okay. According to the American Heart Association, the probability of A, so the probability of a person having a cholesterol level of 240 or higher, is 0.16, so 16%. The probability of B, the person having a cholesterol from 200 to less than 240, is 0.29, so 29%. So explain why events A and B are mutually exclusive. This is a good example to explain what mutually exclusive is talking about. Because you cannot have a person with both high blood pressure, or cholesterol level, and borderline high from 200 to 240 at the same time. A person cannot have a cholesterol level 240 or greater, and then at the same time have 200 to less than 240. Okay, so the events cannot occur together. So in other words, a person either is going to have high cholesterol, or they're going to have the moderate or normal cholesterol, if that's what is considered, okay? So now it says, say in plain language what the event A or B is. That is simply saying a person has either high cholesterol or borderline cholesterol, right? At the event of A or B. So they either have high cholesterol or borderline cholesterol is what they're considering, okay? So that's all that is saying in plain English. If you say A or B in this situation for this problem, A is above or your high cholesterol and B is your borderline. So then it wants us to find the probability of A or B. So to find the probability of A or B, this can also be written, and you will see this be the probability of A or B, okay? It's just like a big U, okay? And a big U stands for or, so A or B. In which case this, because they are mutually exclusive, we're going to use that equation we saw in our big ideas, which in this case is simply saying the probability of A plus the probability of B is all we need to do, because they cannot occur at the same time, so we don't need to subtract anything from this. So we're simply taking the probability of A plus the probability of B. And they told us what those probabilities were. It says up here the probability of A is 0.16, and they told us the probability of B was 0.29, so 0.29. So if we add those together, you should get 0.45. So that is the probability of A or B in a mutually exclusive setup such as this. Alright, so number 3 is saying, let C be the event that the person chosen has normal cholesterol below 200. So not 200 to less than 240, so not a borderline or not a high, but has normal cholesterol, so below 200, and find probability of C. Okay? Well, this is where that complement equation should come into play, right? Because we know what the probability of these other two are. We know the probability of being high cholesterol, and we know the probability of being a borderline cholesterol. Okay, so if we have that, can't we just subtract that from 1? Or if you want to use percentage, if you say it's 45% there for the total we just calculated, we say 100% minus 45%, we should be able to get it. So in this case, the probability of C is simply taking 1 minus our probability of being A or B in this problem, okay? And this is simply saying you have the probability of being normal, right? Normal cholesterol. So we got probability of being normal cholesterol is equal to 1 minus, and we already calculated this as far as being 0.45, so 0.45, and that equals our 0.55. And this is saying that the probability of having normal cholesterol is 0.55, so 55% probability of having normal cholesterol. Okay, so again, now the only thing to be careful with in this situation is if you're using percentages and you wrote this up here as saying 45%, make sure to change this 1 to 100, right? So you're going to say this is 100 minus 45 to get your 55%, okay? I recommend, though, keeping it in decimal format. It makes things a lot easier because problems will get a little bit more advanced and asking for a few more things from them. So leaving in decimal format is the best, but if it's a question that's asking something simple as this, as far as just what is the probability of something for one portion of the problem, you can put in the percentages, it's perfectly fine. But I will accept the decimal format as well and going forward with it. I have no complaints on that. And that pretty much kind of wraps up 4.2 there. So the next one we're going to go into is 4.3, okay? In which case we'll be talking about the two-way tables and our Venn diagram. So for this, I'm going to use some data that I got from a previous class, in which case kind of made things a little bit more fun here, right? So what is the probability that a randomly selected person from class uses Facebook, uses Twitter, uses both, or none? So initially we had collected the data from the class, and I'll go and write in what we got. So with what we got here is, so for Facebook and Twitter, at the time, I believe it was a couple years ago, we did 5. For just Facebook and no Twitter, we had 6. For Twitter and no Facebook, we had 17. Everybody was using Twitter. And then people who used no Twitter, no Facebook was 3. Alright? So when you set up a two-way table like this, or you're presented with one, the best thing to do before you even move forward with problems is go and get your totals, okay? The totals are going to be very important moving forward. So with this, let's say we got, we have 22 down here for this total, 5 plus 17. And we got 6 plus 3 gives us 9. And then we should have 5 plus 6 gives us 11. And then we have 17 plus 3, which gives us 20. In which case, this should mean that they all equal up to the same number, right, for these totals. Total right there should equal the total we did right here, in which case they should all add up to 31. And they do for us, which is good. So we did our math somewhat correct so far. Now suppose that we randomly choose a student from class. Find the following probabilities. So with this, when you're taking just the probabilities, right, you're wanting to do it over the total, right? So the probability of Facebook. So the probability of Facebook is the amount of people that use Facebook over the overall total. So probability people uses Facebook. So we're going to look at this value right here of 11. 11 people totally use Facebook. We went across here on our row 11 out of 31. So our probability is 11 out of 31. Now if we used, let's say, what are we doing here now? Let's do probability of Twitter. So probability of Twitter, so now we're going to look at the column right here, okay? So 5 plus 17 gave us 22. 22. So we're going to simply say we had 22 out of 31 that used Twitter. Okay. Now let's look at probability of no Facebook. The probability of no Facebook, get a different color here. Okay, so probability of no Facebook, so no Facebook is 17 plus 3, so we should get 20 over 31. And then the probability of no Twitter, so no Twitter, we had 6 plus 3, so we had 9. So 9 out of 31 for no Twitter. So number 3 there is asking, now we will find some probabilities for 2 events occurring. So the probability of Facebook and Twitter. Facebook and Twitter. Well, if you look at this, your Facebook and your Twitter. So Facebook going across here and Twitter going down. Well, Facebook and Twitter is right there at 5. So that box that intersects both those for Facebook and Twitter is 5. So 5 out of 31 did both of those. Now the probability of Twitter and no Facebook. So just Twitter going down on Twitter but no Facebook. So we're going to go with 17 out of 31. Then we're going to look at probability of Facebook and no Twitter. So Facebook now, we're going across on the row here, and then no Twitter, so we're going to say 6 out of 31. And the probability of no Facebook and no Twitter, so no Facebook, no Twitter, we saw we had 3 people that did no Facebook, no Twitter. So the probability of that occurring in that class was 3 out of 31. So now let's look at number 4. It's asking for the probability of Facebook or Twitter. Okay? Does that equal the probability of Facebook plus the probability of Twitter? Why or why not? So let's see. How do we need to solve this? What would be the equation we use? Are they mutually exclusive? Not necessarily, right? Because they could occur at the same time. We just said we had a probability of Facebook and Twitter. So they can occur together simultaneously. So therefore it's not mutually exclusive. So in the equation that you guys should have had up there in the big ideas, it should show that if we have the probability of doing Facebook or Twitter, we should have to take the probability of getting Facebook plus the probability of Twitter, and then subtract, because those, we'll show you in a second, we're going to subtract the actual probability of Facebook and Twitter. Probably Facebook and Twitter. Now, and is like a lowercase n. You can write out the word and, or you can write just a big lowercase n there for, or a horseshoe effect, however you like to look at it like that. Rainbow, whatever you want to call it, okay? So Facebook and Twitter. Now the reason why that is because let's look at this. If we did the probability of Facebook, in which case we got that up here, right? Probability of Facebook was 11 over 31. And then we took the probability of getting Twitter. Well, the probability of getting Twitter was 22 over 31. And now we're going to do something real quick. Let's look at this real quick. If we did, let's say, we did the probability of getting Facebook, right? So we used this value, right? So as we added up these two values to get this value. And then, let me scroll up a little bit. And then to use Twitter, the probability of getting Twitter we said was 22 out of 31. So if we added 5 and 17, that's how we got 22. Well, what number do we use twice in getting that value? We use the probability of Facebook and Twitter, right? We use that 5. We use that 5 twice. So therefore, then we have to subtract 5 over 31. So therefore, it's not counted twice. In this, we should get 28 out of 31. (28 over 31) is what your probability of being Facebook or Twitter, because this is not mutually exclusive, right? So this would be a double count. Therefore this one, no. We can't just add the probability of Facebook and the probability of Twitter, because there would be a double count. Because double count of probability of Facebook and Twitter. And we don't want to do that, okay? So now let's see about putting this in a two-way table down here, getting this all squared away. So take the values from the two-way table and put them in the Venn diagram, okay? So, as we saw in our big ideas, go back here to big ideas, let's look at this. So, we should be able to put 1, 2, 3, 4 if we have A and B, not A and not B, and it should play out just like this, okay? It should make perfect sense. Well, let's see. Sometimes it confuses people, even myself. Alright, so now, with this one we're doing Facebook and Twitter. So that one that I circled right there, that we did twice when we did for Facebook or Twitter, that is our value of Facebook and Twitter. So we should know that we have 5, because we have Facebook, this circle, and we have Twitter, where they overlap, the value was 5. There was 5 people that did Facebook and Twitter. Now, what was left over here as far as then just who was on Facebook, if we scroll a little bit more, if we look at that, just for our Facebook, going across the row here, we had 5 plus 6 that did Facebook but no Twitter, and it made us 11. So therefore, if it's just Facebook and not included in the Twitter circle, there was a 6 here, because 6 of them did Facebook. Now, if we go on the column here for Twitter, we saw 5 that did Facebook and Twitter, which we already have that here. And then there was 17 that did Twitter but not Facebook. So the value that should go here and just in the Twitter bubble and not Facebook is 17. Now, the last number we worry about is what value is outside of those, the Venn diagram. In other words, what values, in this case, did not do Facebook and not do Twitter? Well, in our little two-way table up there, we see that value is the number 3. We see that number 3 is our value that did neither Facebook nor Twitter. So, 3. So in this case, where it's asking there for where is Twitter and Facebook, well, we already kind of determined that, right? Twitter and Facebook is right there in the middle, so it's in the center overlap. Center overlap. Okay, and then where is Twitter or Facebook? Well, if you're doing Twitter or Facebook, that is going to add up. Let me change colors here real quick. Twitter or Facebook is going to be adding up these 3 values. It's going to be everything inside of the circles. So, inside either circle. And you should be able to see that. We would get very easily, you should be able to get 6 plus 5 plus 17, and that should give us our value of 28 over 31. So if you're able to draw this Venn diagram out, it should make perfect sense for that and going forward with it. So again, guys, definitely look at these big ideas that we went over and covered today. Again, start kind of understanding what the complement is referring to, the equation, get that ingrained in your brain as far as mutually exclusive as well. Again, that's 2 events that cannot occur together. So in the case of the cholesterol, in the example we did, right, you can't have high cholesterol or borderline cholesterol or normal cholesterol all at the same time. Those events are all mutually exclusive. However, though, in our last example we just did with Facebook and Twitter, they can occur at the same time. You can look at Facebook and you can look at Twitter, right? So with that, definitely just think about it. You kind of got to think outside the box there for a minute when you read some of these problems and ask yourself those questions. Can this occur together or can it not? And that's what you need to take away from that for sure. Also, make sure to understand the two-way table. Again, the totals are very important to calculate on the sides. and then calculating or being able to put that into a Venn diagram is very beneficial as well. You will need to know that for sure for upcoming tests, quizzes, homework, things like that. Alright guys, hope you learned a little something today, and I'll see you next time.